Calc BC students, it's Mrs. Allen, and we're here to talk about section 9.5 and finding the area of a polar region. This section also has the arc length. If we have time to do a couple problems with that, that'll be great. If not, it's not tested on the AP exam, so I'm going to have to let it go given time constraints. But we start off, the development of the formula for the area of a polar region parallels for that of the region of the rectangular coordinate system. The primary difference is that in polar, we use sectors instead of circles. Now, we already spoke about this, but you can see a pink sector over here in the left-hand side where you can see that the angle theta sweeps through an angle, and then you have an arc length S on the end. So remember, you can find the arc length by doing S is equal to R theta. But to find the area, it's 1/2 theta R squared. So, and that's when theta is in radians. But so we can use sectors of circles with this, and think of when we were dealing with Riemann sums before in Calc AB and some in Calc BC, that we were adding up rectangles. So we're doing the summation of rectangles, where now we're going to sum up these sectors. And you can kind of see in the pictures that I have inserted here, here's the purple one to the right-hand side, where you can see that we're going to add up all those little sectors. And though they are approximations, you can see that you might have an overestimate or an underestimate, but nonetheless, you still have an approximation. But once you increase the numbers, then you'll have the exact area. So you increase the numbers of sectors, and then you have the exact area. And we want the number of sectors to go to n goes to infinity, okay? So consider the function given by r is equal to f of theta here, f of theta, then where f is continuous and non-negative on the interval. So it can't be negative. F can't be like a negative value. So we have the interval given by from alpha to beta, the region bounded by f and the radial lines theta is equal to alpha to beta. So they're like our A and B for the limits of integration. And it's not a strange thing that we use alpha and beta. They're the Greek letters, the first two letters of the Greek alphabet. So that's alpha and beta is what we wish to find. So the region bounded by alpha and beta, you can kind of see here. Here's highlighted, there's alpha, and then beta is then above it, going counterclockwise. So if we partition alpha to beta into n subintervals, where you see that you have these theta sub zeros, theta sub 1, theta sub 2, then we let the radius of the ith sector be f of theta sub I, and the central angle of the ith sector to be b minus alpha over n. That's going to equal our delta theta. So you see that we can see our Riemann sum, not with rectangles, but with sectors here. So you have the summation of 1/2 delta theta times r squared. R is f of theta sub I squared, and I is the counter from 1 to n, same as Riemann sums. Okay, so then you have this formula where then the A is equal to the limit, and then that's equal to 1/2 the integral from alpha to beta of f of theta squared d theta, where r is equal to f of theta, then we have this 1/2 of the integral from alpha to beta of r squared d theta. And then if f is continuous, here is the theorem, the area in polar coordinates. If f is continuous and non-negative, on the interval from 0 to 2 pi, beta minus alpha, then the area of the region bounded by the graph of r is equal to f of theta between the radial lines, alpha and beta, is given by that formula, okay? So I have example 1 that I'd like to talk about first, and then noting that we did this graph on the previous lesson, graphing a 3-petal rose, so very similar. The 3-petal rose, and you should keep that chart kind of handy in terms of what the graph looks like until you get used to it with all the cardioids, lemnicons, lemniscates, roses, and circles. Okay, so making sure you review that from the 9.4 notes, graphing polar graphs. So here's what we're going to do. So you might wonder, and we talked about it a little bit, how do we get the limits of integration for this? How do we set this up? So noting that alpha is the upper limit, beta is the lower limit, right? We start off with our formula in step one. I'm going to use a green highlighter here. So there's step one. We write our equation, noting that this problem says find the area of one petal of the rose curve given by r is equal to 3 cosine 3 theta. So we have r. Now notice I have alpha and beta already, and here's the rule for finding alpha and beta. We watch the behavior of the curve. If I start off at theta is equal to 0, use highlighting 0 here. So I start off at theta is equal to 0. And notice that I get 3 times 0, which is 3 times 1, or 3. So I have that first point A, 3, 0. And then I watch the behavior of the graph by going forward. And cosine is compatible with pi over 3, right? Pi over 2. So I look for a compatible angle to put in. I notice that if I put pi over 6 in, I'm going to get cosine of pi over 2. So I'm going to put pi over 6 in. And I note that the behavior of the graph, it travels. So as I'm going from the first point at 3, 0, it travels to the pole at point B. So the radius is 0 at that point, but the angle is pi over 6. Now there's a theorem that states that if you have a point on the polar graph that is at the pole, then the angle is actually tangent to the polar graph at that point. And you can see that. I think that was in the 9.4 lesson. So I know that I'm at 0. And then upon looking at this further, as I go around, I see the behavior of the graph goes like this, right? So it's continuing to go, and it, kind of like we did in class, your movement goes like that. I only want to find the area of one petal. Now, if I wanted to find the whole thing, it's going to turn out that I could multiply the area of the one petal by 3 to get the area of the whole graph. Upon investigation with this, the rose goes through a complete cycle of the graph. It's traced out from 0 to pi. So if I go from 0 to 2 pi, then I'm going to trace through it twice. I'll go through twice the area. So kind of an interesting dilemma we get in. We've got to kind of figure that out. So I've got that. I need the one petal. So upon investigation here, you see I have the negative pi over 6. So as I come back around here, I can actually take the integral then from negative pi over 6 to pi over 6 for my alpha and beta limits. And that'll give me the region or the area boundaries for the angle theta, okay? So as you look at the point here, getting back to that point after I go all the way through, let me highlight this, kind of knowing what I'm talking about here. I'm going to start here and I'm going to go through, I'm going to sweep through, and once I get to here, I'm back at 0. So whatever angle I'm at that point, then I'm gonna go back through, and it turns out that I'm at 5 pi over 6, right? So, and then at pi, I'm back, if I do 3 pi, I'm back at the point 3, 0. I'm thinking for just a minute how I'm going to do that. Even though, since I'm at pi is over here, it would really be a negative r value that would put me back there. So what I want to do is understand that, okay, if I start at pi over 6, I can actually go backwards pi over 6. And so that's why I'm starting at negative pi over 6 here. I'm going to go from negative pi over 6 to pi over 6 because I need the angles to sweep through in a way that you're going in incremental steps to the next angle. So in other words, I can't use 5 pi over 6 there, okay? I'm not going to go from 5 pi over 6 to pi over 6. So I've got to back it up and say, well, what would that angle be? So from negative pi over 6 to pi over 6, I have my setup, okay? So that would give me the tangent lines, tangent to the pole. So I then set up my integral. I put my r value in. So 3 cosine 3 theta, I'm going to square that. I've got negative pi over 6 to pi over 6 for my alpha and beta. Then I square the 3 cosine 3 theta. That gives me 9 cosine squared 3 theta. Then I'm going to pull the 9 out front. Pulling the 9 out front. So now I have 9 halves times the integral from negative pi over 6 to pi over 6 of cosine squared 3 theta. Now, with a cosine squared, this is a power reduction formula. So when you see this, I've got a little star down here again, but I think I mentioned it on another video that you'll see this. I keep mentioning it. This is a power reduction formula where I have cosine squared u is 1 plus cosine 2u over 2. And our u in this case is 3 theta. So when I plug this back in, the 2 times 3 theta is going to be 6 theta. So if you notice what I have here now in the next step is I have 9 halves times the integral, and the integrand becomes 1 plus cosine 6 theta over 2. I'm going to pass the 2 out front now, so I only have an integrand in the next step. I only have an integrand of 1 plus cosine 6 theta. I've pulled the 2 out, making it a constant multiplier of 9/4. Then I'm going to go ahead and take the antiderivative. With the antiderivative of 1 is theta. Remember, it's d theta. And the antiderivative of cosine 6 theta is 1/6 sine 6 theta. So remember, p is, I'm just saying it's a p antiderivative, if you will. So then I'm going to evaluate the antiderivative at pi over 6 and negative pi over 6, and I'm going to subtract them. So that's what I do in this next step. And sometimes it's kind of nice when things like this happen. You evaluate it and you take a look at it. Before you start doing all this kind of fancy math, you might go, oh, those 6's are going to cancel with the angle. 6's, oh, that's pretty cool. Because if you look at it, 1/6 sine of pi is 0, so that whole term goes to 0. And then you can see inside of here that this whole term is then going to go to 0 with that, because this is all going to go to 0. Because it's going to be the same thing. Sine of negative pi is still going to be 0. So then it turns out it cleans up pretty nicely, right? So you have 9/4 times pi over 6, and then that's going to become a plus. This is going to be plus pi over 6, right? So plus pi over 6. Okay, so then we get 9/4 times pi over 3. Pi over 3. And what we're going to do is cancel the 3 and the 9. When we do, we get our answer. 3 goes into 9 3 times. So we get this is equal to 3 pi over 4. Always a good idea when you have a calculator available when you're working on problems is to kind of check to make sure that you get the right answer. So you're going to get something like 9/4, which is about 2.2. 9/4 is 2 1/4. So it should be somewhere around that ballpark when you test it. So be careful that when you're checking it, you should actually check out the values of this. If you go from 0 to 2 pi, or if you check this out and do the integral, the complete integral from 0 to pi, what happens? And see if you can't reason what is going on, okay? And with that, I'll pick up with example 2, and I hope you guys have a great evening, and I will see you in class. All right, so take care. This is Alanator out with example 1, 9.5. All righty then.